Good morning. Let me introduce a new topic after bearing capacity. This is a new topic is settlement of foundation, and you know that when a footing is let me go to the next slide and then I will show you. Suppose there is a footing, suppose like this, and it is loaded, and then you will have, because of this loading, that bearing capacity failure is one possibility if the load is excessive, and another possibility is that because of this loading the foundation will move downward, and because of the compression of the soil in this zone, and this compression because of many reasons, and some of the things I have discussed in the soil mechanics also, and you might have read some in the previous courses, and that this compression of the total compression what we will see at the surface will be consisting of three components, and they are actually. This is the one, that means it will be consisting of three component as I have already mentioned. And suppose if there is a surface movement because of this foundation, that movement is total, suppose delta, and since I have mentioned that delta will be consisting of three parts, and they are actually, this is one part, this is another part, that this is another part. So, delta F, that means delta footing or delta final also sometimes say, the final settlement will be delta I plus delta C plus delta S. Delta I means it is a immediate settlement. Immediate settlement will happen because of the elastic property of the soil. Like a member, if I pull, if there is a circular member like this, if you pull or push, then because of this either tensile or compressive load, either it will elongate or it will compress. Similar to that, when the load is applied to this soil, it will be subjected to compressive load, and under that compressive load, and because of the elastic property of the soil, there will be some compression, and that is called immediate settlement. And then another thing is, if the soil is fine grained and saturated, and when you apply load, then I have discussed in the beginning also in the review of soil mechanics, that there will be a consolidation mechanism will appear, and that consolidation mechanism is what actually because of this loading, that your pore pressure within the soil will be developed, and then with time that pore pressure will be dissipated, and then that extra load will be transferred to the soil grain. When the load transferred to the soil grain, then the soil grain will be pushed towards each other, and then and that result in actually compression and that reduction in void ratio. That delta C is the consolidation settlement that happens because of the reduction in void ratio of the soil mass, and that is a property the mechanism will be there for saturated fine grained soil. And another is delta S, that is after completion of the consolidation settlement, still after a long time also there may be some amount of settlement, and that is called secondary settlement, and that happens because of many reasons, creep and other effect. So, these three parts actually will be the total settlement of the foundation. If the soil is only on sand, then we may not see the consolidation. Again, if it is on the only clay, and then if the clay soil, then elastic also will be there, it will be small, but consolidation will be major, and this also may be there. So, like that, depending upon your soil type, different parts will have different magnitude. So, if I summarize that, then you can see here that it is given soil type, and it is sand, steep clay and soft clay, and percent of rho f, that rho, it is not rho since I have used delta. So, this is delta, percent of delta f due to delta I. So, that means delta I means immediate settlement. So, when it is sand, the total settlement will be consisting of 70 to 80% because of the elastic settlement. When it is steep clay, it is 50% elastic settlement, 50% maybe around consolidation settlement, and if it is a soft clay, then it is 10 to 25% is elastic settlement and majority will be consolidation settlement. So, that means now the foundation can be resting on different type of soil at different groundwater condition, and because of that if I apply the load, then you have settlement, and that settlement can be of combination of delta I, delta C and delta S. So, that means we have to learn to find out how to find out delta I, how to find out delta C and how to find out delta S. And let me show you the next slide, and you can see here that is another point I want to highlight here, that as I have told that there are three components delta I, delta C and delta S, and if I plot this total consolidation total settlement over time, then you get a plot like this. This is time axis, this is time, and you can see this is total settlement of suppose foundation delta H, and then you can delta H, and this is actually delta I. This small portion is because of the it can be more also with some soil, but suppose it is a C5 soil, then your delta H I is this much and time is this much. That means, immediate settlement will happen actually immediately, very little time, whereas consolidation settlement starts from here and maybe end of consolidation may be here, and that means from here to here is the consolidation settlement. That amount is generally large and fine grained soil, and you can see to complete the consolidation it starts from here and end here, that means there is a long time. The consolidation settlement is a time dependent, that is generally several years it may take some time, and you can see the beyond this end of consolidation the foundation may further undergo some amount of compression, and you can see very mild slope, it is going downwards, and that means with time there may be some amount of settlement, that is because of creep and arrangement of particles etc., and that actually you can see delta S, that amount is quite small again, and time actually you cannot predict, actually you can estimate at maybe 10 years or 20 years, then accordingly we can estimate how much it will be. So, it's supposed to be continued for long. So, that means from this figure I wanted to highlight that the foundation settlement will be consisting of three parts. One is immediate settlement, consolidation settlement and secondary consolidation, secondary compression, and this immediate settlement will be immediate by the name itself, or it is called elastic settlement, and consolidation settlement is a time dependent, it amount sometime it will be large for some soil and it will be for a long time, over a long time it will happen, and secondary compression also after end of consolidation still may be further compression, and that with time how much that can be estimated, there are some methods. So, we will discuss that, but here I wanted to point out that this consolidation settlement is a time dependent and immediate settlement is the quick, means immediately after loading, and secondary compression sometimes is not that important, most of the time we do not compute, we do these two. So, we will try to learn these two aspect elaborately, and you can see now which I have discussed also in the soil mechanics, and also you might have learned from some other books and other, that when there is a load applied on the surface, and if I consider a axisymmetrical case, and then there will be component of forces, there will be vertical force, vertical stress, there will be sigma t, sigma r, then tau, and all these things will be there. And if I consider one element, So, somewhere here, and that strain on that element will be can be written in this by this equation, and sigma z is the vertical stress component, sigma r is the radial component, and T is the tangential component. So, these three component and for axisymmetric case sigma r and sigma t is equal, then you can further modify this into this form. Now this epsilon at a particular point, and if I integrate that epsilon, that strain over the depth of the soil, then I can get the total settlement. This is for elastic. I am considering now elastic only. Assume the soil is elastic homogeneous subspace and there is a load applied on the surface, and because of that loading at a particular point I am trying to find out the strain, and then I am trying to find out the settlement by integrating over the depth. Suppose the soil is extended up to this, then I will be integrating from 0 to, suppose this is theoretically infinity. So, that actually I can integrate, and this is a detailed mathematical procedure, and it is a theory of elasticity, can be book can be read for details. But finally, if you do, if sigma r, sigma z, whatever given by the Bouguereau, if I substitute here and integrate by this way, then finally you get a settlement expression similar to this. So, you can see here the q is the if there is a footing here, then that q is actually pressure applied on the soil through the footing. So, this is q, and b is the width of the footing, and E is the Young's modulus of the soil E, and mu is the Poisson's ratio, and I is an influence factor, and this influence factor actually to incorporate that the footing shape may be circular, strip, rectangular or any other shape, and also similarly footing can be of flexible type or rigid type. So, to consider those effect, considering all those things, this I can be brought here one factor. So, q b by E 1 minus b, these are the things are known, and this is the thing to be calculated. In fact, if you integrate this for different soil foundation shape with different pressure distribution, we can get different expression, but those expression finally expressed in a generalized form, keeping this only one unknown is kept, and that one unknown actually for different soil or different different footing size or different pressure type, this will vary. So, I will go to the next slide and show that. You can see here that expression delta equal to q b E by 1 minus mu square I, and q is the contact pressure below the footing. That means, if the footing is here, so through this footing what is the pressure, that is q, and b is the width of the footing. If it is a rectangular, then it is a smaller dimension. If it is strip, the width of the footing, it is square, it is the width of the footing, and if it is a circular, it is diameter of the footing. And E is the Young's modulus, and mu is the Poisson's ratio, and I is the influence factor, depends on shape and type of footing. Type of footing means whether it is rigid or flexible or some other in between. So, this is the expression we can use for finding out settlement. So, that means I need actually, if I want to estimate for a particular footing for which loading is known, Young's modulus of soil is known, Poisson ratio is known, I need actually I. For that actually there is a different people actually over the time calculated those, integrated and finally given the value, and you can see if the type of footing, if the rigid footing, if the footing is rigid, and then again type of, as I have told you that I is function of footing type and shape. So, again now circular shape, it is a rigid footing of circular shape, then I will be 0.79. If the rigid footing of square shape, then I will be 0.82, and rectangular footing with L by B is 2. L by B is 2 means this is like this. If this is L and this is B, so L by B actually 2, then this I is 1.12, and rectangular footing again with L by B equal to 5, 1.6, and L by B actually 10, then it is 2, and in fact, if the L by B become more than 10, better to assume as a strip. So, up to that actually I have given the value. So, that means, if I want to find out a footing of rectangular footing of L by B equal to 2, L by B equal to 2, then I will be getting the delta will be equal to Q B 1 minus mu square multiplied by I will be directly I will take 1.12. Similarly, if I want to find out L by B equal to 5, then it will be same Q B 1 minus or Q B by E actually Q B 1 minus mu square by E multiplied by 1.6. So, like that I can easily find out using these values. Similarly, if the footing is flexible, if the flexible footing and again different shape, if it is circular, then when the footing is flexible, actually settlement will not be same everywhere. When the rigid footing, the settlement is same everywhere, and when the flexible footing, settlement in different places will be different. And you can see the expression we have got. According to that expression, I actually for circular footing is maximum I is 1, for square footing maximum I is 1.12, for rectangular footing with ratio 1 2 maximum I is 1.5, rectangular footing with L by B equal to 5, the maximum value of I is 2.10, rectangular footing with L by B equal to 10, there actually maximum value is actually 2.5. So, sometime since a different point actually different settlement. So, because of that, instead of using that maximum value, sometime we may take average value, which will give you better design. So, sometime that there is a some people actually given this average value also. Average I for circular footing is 0.85. That means, for a flexible footing, if I want to find out circular flexible footing of diameter B, then I will get delta will be equal to Q B divided by E multiplied by 1 minus mu square multiplied by 0.85 0.85. So, instead of I could have taken I can work also based on maximum value, then I will use 1, but if I want to use average value, then I will use 0.85. So, this is the way one can find out. Similarly, if they want to use want to estimate settlement, immediate settlement or elastic settlement for square footing of width B, then I can find out delta will be equal to Q B by 1 Q B by E 1 minus mu square multiplied by a maximum, it will be 1.5 square, it is then 1.12, and if I want to use average value, then I will use 0.95. So, like that, by this equation and combination of this equation and this table, one can find out the elastic settlement of the footing if you know the width of the footing and elastic modulus and Poisson ratio of the soil is known. So, this is actually when actually the footing is resting on homogeneous elastic half space. What is the meaning of it? That means, your footing is here, and suppose and this one up to a great depth the homogeneous same soil is there, and in that case that means we have integrated 0 to infinity. So, that theoretically we assume that a soil is same up to the quite large depth, but sometime in actual in the field condition, there may be multiple layers below the footing, and also it may be up to some depth the soil, and then there may be rock. That means, there is a soil layer is a finite. In that case, we will not be able to use that equation, because the I is obtained based on the integration from 0 to infinity, whereas from some depth to infinity, that some depth, that is actually soil is not compressible. If it is rock, incompressible if I consider, in that case that will not be applicable. So, for that actually to find out the settlement or resting of footing resting on a finite layer of soil or on resting on a multiple layer of soil, then we have to use some other method, some other technique, and that technique is suggested by Smartman. That is actually, this is the name of the person, Smartman, who has suggested this method, and I have shown that your epsilon equation equal to sigma by E minus 2 mu by E into sigma r. Okay. And then what is this? This below the footing, just close to the foundation and below, at sigma r has some value, significant value, but if you go a little deeper like 0.5 b or beyond, then this sigma r value is very, very small. Okay. So, because of that, in the contribution of strain, effect of this may not be that significant and can be ignored. So, simply I can do epsilon equal to sigma by E. If I know the vertical stress and divided by E, if I do, then I can get the strain, and again if I integrate this strain, then I will get the compression. There I am just ignoring some portion, and which will be actually favorable. So, because of that, considering this concept, the Smartman or this observation, Smartman suggested this method. Again, for developing this method, what he has observed, that he has tried to see the vertical stress distribution when you apply the load on the surface. When you apply load on the surface through footing, how pressure distribution will be there below the footing. So, that he has tried to observe, and he has seen the pressure distribution something like this. It is a curve, at some depth it become maximum, and close to the surface some finite value, and at some depth it will become 0. So, based on this observation for different size of footing, he has suggested two model. One model for strip footing, you can see for strip footing, this is the model, and in this actually what he has given, that this is actually, this line actually it is just base of the footing, base of the footing. From here he has given a diagram, at the base of the footing value is 0.2, and at a depth of b, that is influence factor, that is I e max, I epsilon max, and at 4 b depth, that epsilon, that strain, because of the load applied at this surface at 4 b depth, suppose strain is 0. So, that is the concept he has used, that surface it is 0.2, at b depth that is I epsilon max, and at 4 b depth it is 0. And he has given the value of I epsilon max in terms of 0.5 plus 0.1 under root q effective by sigma b dash, and q effective is effective equal to q f minus gamma d. Q f actually, if it is a through the footing, if you applied pressure is q here, and since footing is placed at a depth d, so gamma times df can be subtracted to find out q effective. So, if you know the q effective, and then sigma b dash is what? At b depth from the footing base, what is the effective stress that to be obtained. So, if the footing is here, and if the footing is here below, from the below the footing at a b depth, what is the sigma b dash effective stress. So, that to be calculated, and q effective to be calculated, and then using this equation one can find out I epsilon max, and then I will get this diagram. Okay. So, I will get the 0.2 here, at b depth is this much value, and at 4 b depth is 0. So, then I will get this diagram. Once I will get this diagram, So, everything is clearly written here. Sigma b dash is vertical effective stress at a depth equal to b from the base of the footing or df plus b from the surface. That means, if the footing is somewhere here, suppose footing is here, then I am taking the I max will happen at this depth actually b. So, b from the base of the footing or df plus b from the surface of the footing. If the footing is on the surface, then it will be simply b, and if it is b is at a footing is at a depth d, then it is df plus b from the surface, but if I consider from the base of the footing, it is b. So, that sigma b to be calculated, q effective to be calculated, I e max to be calculated, then complete this diagram. Once this diagram is completed, then using this diagram how to find out the settlement I will come later on, and this model is applicable for only strip footing. Similarly, he has given for a another type of footing, that is which is applicable for square and circular or circular footing, and this is the diagram. You can see here this value is missing, this will be 0.1, and you can see the diagram is almost similar, only the value is changing. You can see there actually at b depth from the base it was becoming I e max, whereas here in the circular and square footing it is becoming maximum at b by 2 depth. That is only one difference. There actually value was surface value was 0.2, here surface value is 0.1, that is second difference, and there actually final strain becoming 0 at b depth, and here actually 4 b depth, and it is actually here at 2 b depth. There it was 4 b depth, here it is at 2 b depth. So, three differences, one is this value at the surface I e max at b by 2 depth instead of b depth, and I strain 0 at 2 b depth instead of 4 b depth. So, these are the three changes. In addition to that, I e max equation also minor difference, it is 0.5 plus it was 0.2 times this, but it is 0.1 times now, since the value is 0.1, and q effective is same q f minus gamma d f, and this sigma b dash also same at a sigma b dash is here also different, because sigma b dash instead of sigma b dash I can write sigma b dash sigma dash b by 2, because it is from the b by 2 from the base, because I am trying to find out maximum from b by 2 from the base of the footing. So, these are the things. So, if the base of the footing is a b by 2, but if I want to find out from the surface of the footing, then df plus b by 2. This has to be remembered very carefully. So, that once you know these two model, using these two model one can find out the settlement using this equation. This is actually final expression of settlement equal to delta equal to C 1 into C 2 into multiplied by Q effective sigma I E I H I divided by E I. And what is I E I? So, diagram was like this, your diagram was something like this, but in this different layers may be there. So, different layer, what is the value of I I? So, that means I E I multiplied by thickness divided by E. So, that way we will get the settlement of particular layer. Similarly, if I go to second layer, so I E 2 multiplied by H 2 divided by E, and then you will get second layer. So, like that all if n number of layers are there, so n number of component will be there. So, that to be summed it, and that multiplied by Q effective multiplied by C 1 multiplied by C 2 will be the total settlement. And C 1 expression is given like this, C 1 is equal to 1 minus 0.5 Q s by Q effective. Q s is the pressure through the footing is applied, and Q effective already I have mentioned, and C 2 is 1 plus 0.2 log 10 t, and t is the time. That means, this is because of to introduce the secondary or long term settlement. That long term settlement can be estimated by using this expression or factor for long term settlement, and 10 t is given. T is time, in year actually. If it is said that what is the settlement after 6 months, then it has t to be taken as 0.5. If it is mentioned that after 10 years, then t will be taken as 10. So, by using this equation I can find out C 2, by using this one I can find out C 1, and from the using the previous diagram I can find out this component, and then this will become the total settlement of the footing, elastic settlement. So, with this I will stop here. Thank you.